Good morning. Thought I'd make a quick video this morning about a new circuit that I've developed. It's for Class AB biasing of RF amplifiers. Actually, I have a circuit that I'm currently using on a current amplifier version that is very similar. But this new circuit uses a precision gain op amp to do some of the work of the bias system where this amplifier doesn't have it. The biasing in this amplifier actually works quite well. It regulates the bias to about 15% or so over a -20 to 100 C temperature range, which is very respectable. But we're trying to improve on that a little bit, and so I've changed the design. This is the new design. I'm using it on this old prototype 2-transistor amplifier, very similar to the one that you just saw. And this over here is the circuitry involved for the bias, as well as the op amp over here on the breadboard. This is the adjustment for the biasing. So what we've done here is, or what we're going to do here today is, we're going to show you just how the bias corrects over temperature, over the temperature range. Okay, now right now we're at room temperature. I've got this heat sink stood off of this pad here because we're going to heat this thing up here in a few minutes, and I don't want to melt the pad. But anyways, I have the amplifier standing by now. We're not going to put any RF into it or anything like that. We're just interested in looking at the bias right now on these two devices and making sure that it's constant over temperature range. Of course, you know that if you don't have any thermal compensation, what happens if you try and apply bias to these transistors or any bipolar transistors, when they get hot, they have a tendency to go into this thermal runaway condition where the bias current increases dramatically. And what happens is, as it gets hotter, it increases more, and then it gets hotter and it increases more, and finally what happens, the ultimate result is you burn up the transistors. So we don't want that. So we're thermally compensating for that effect. Okay, so what we've done here is we have our power supply on right now over here, and we're powering up this amplifier. Like I said, we're not going to put any RF into it or anything like that. We're just interested in the DC biasing, the collector currents on these two devices. We're monitoring that right now via this meter, and we're set up right now for 200 milliamps, and you can see it flickering between 199 and 200. Okay, so we're standing by right now, 200 milliamps, room temperature heatsink. So what I'm going to do now is I'm going to heat the heatsink up with a propane torch to get it going quickly here. And what you're going to see here is, I'm going to explain what's going to happen. What you're going to see is, you're going to see this runaway effect take place, because I'm going to heat the heatsink over here on this end, and the heat will spread out going this direction. And what happens is, it will get to the transistors here first. They will start to increase the bias current. You'll see the bias current jump up dramatically. And what happens is, as the heat progresses through the heatsink and finally gets to the correction devices over here, and of course they're also working with the op amp on this board, what you'll see is you'll actually see the collector currents start dropping back to where they were originally, to the 200 milliamp range. That's what we're trying to do here. We want to try and hold this 200 milliamp bias current no matter what the temperature of the heatsink is. So let's get going, and we'll heat this up, and I may have to put the camera down here so I can light the torch, and this is going to be a little tricky here, but okay. Okay, let's see if I can do this with one hand. Okay, we have our propane torch here. We got it lit up, and what we're going to do is we're going to start to heat this right side of the heatsink. You can see that we're still at 200 milliamps, and I'm going to start heating the heatsink here. And we'll watch the current meter now, and we'll notice that in a few seconds you'll see the current start to rise. Now you see we're already over 400 milliamps right now on the bias, so it's already doubled, and you can see it's going up quickly. Okay, now we're going to take away the heat. Okay, and we're going to watch now as the heat spreads through the heatsink. Now it will finally get to the devices. You notice that we're still going up now. And in a few seconds, you'll see when the heat finally gets to the correction devices, the current will actually drop back and start moving back towards the 200 milliamps. There we go. It looks like it's slowing now. Okay, now we're going back. Now the correction is taking effect, and you'll see that as those two devices over here on this side start to get some of the heat that's coming across the sink, you'll see it's dropping back now. Now unfortunately this heatsink is pretty big, so it takes maybe 3, 4, or 5 minutes or so to actually stabilize so the entire heatsink is the same temperature. But if we were to wait that long, you would see that, oops, meter shut off. You would see that the current would actually drop back almost exactly back to the 200 milliamps. So even though the heatsink now is much warmer than it was before, that the current is moving back now, and you see what would have happened if you didn't have any correction. The bias current can actually go to many amps if the heatsink gets really hot, and it'll just blow those devices. No doubt about it. So you can see it's still moving back now. Like I said, if we wanted to wait, which we don't, for the entire 3 minutes or something like that, you'd see it go back. Actually, it goes back. This circuit is about moving back to like approximately about plus minus 20 milliamps from the target 200. So that's pretty darn good. That's about 10% accuracy at the 200 milliamp level. So that's darn good. So this is working well, and that's what temperature compensated Class A B bias is all about. Thanks for watching.